We're given the integral x squared dx over the square root of 1 minus x squared, and we have a pattern of a squared minus x squared in the denominator, and that indicates usually a trig sub. And so what we can do is we can recognize that we have a subtraction symbol here, and that indicates that our trig sub will be a sine or a secant, and because we have a before x, that shows us that it will be a sine trig sub. And so what we have is x equals a sine theta, and in this case a is the square root of 1, which is just 1, so we can say x equals sine theta, and in this case the derivative of x is simply cosine theta d theta. And we can use this information to fill out our integrand, so we can rewrite this as the integral of sine squared theta cosine theta, pulling this sine and squaring it there, and then pulling the cosine from dx and replacing it here, over the square root of 1 minus sine squared theta d theta. Now, of course, using our Pythagorean identities from trig, we know that 1 minus sine squared theta is simply cosine squared theta, and because it's under a radical, we know that that simplifies even further down to cosine theta. So this can all be rewritten as the square root, or the integral of sine squared theta cosine theta over cosine theta d theta. The cosines here will cancel, and so we really have the integral of sine squared theta d theta. And of course now we have a squared trig entity, so we'll have to perform a step down using a double angle identity. And for sine, that looks like a minus rather than a positive, because the positive would be for a cosine squared function. And so we can rewrite this as the integral of 1 minus cosine 2 theta over 2 d theta. We can kick the 2 out front and rewrite it once more as 1/2 times the integral of 1 minus cosine 2 theta d theta. And now we're ready to go ahead and integrate. So we can rewrite this as 1/2 times now the integral of 1 with respect to theta is simply theta, minus the integral of cosine 2 theta with respect to theta, of course, is sine 2 theta over 2. And this is an integral with no bounds or limits, so we must remember to add a constant at the end. And finally now, we have terms that are in terms of theta. We need to remember that we started this question in terms of x, and so we'll have to pull this substitution here, x equals sine theta, back down here. And so we've got x equals sine theta. The next thing I'll do is I'm going to recognize that sine 2 theta is the same thing as 2 sine theta cosine theta, and so we can rewrite this as 1/2 times theta minus 2 sine theta cosine theta over 2 plus a constant, and these 2's here cancel. And now we can solve for theta. So we can recognize that sine theta, which we have here, is just x, and we can recognize that theta in this case equals arcsine of x, and that we can put here. And so now we just need to solve for cosine theta, and we can do that by drawing a triangle. So we'll use this angle here as theta, and we know that sine theta equals x, sine of course being opposite over hypotenuse, and so we'll have x over 1, and we'll call this y for now. And if we solve for y, what we get is 1 squared equals x squared plus y squared, and so y equals 1 minus x squared under a square root symbol. So we can rewrite that here, 1 minus x squared. And so cosine, of course, is adjacent over hypotenuse, and so cosine is just the square root of 1 minus x squared. So now we can come back here, we can say 1/2 times, and remember theta is arcsine x, minus now, sine of theta is just x, times the square root of 1 minus x squared for cosine theta. And now we must remember to add our constant, and all that's left to do now is to distribute this 1/2. So what we've really got is arcsine x over 2 minus x times the square root of 1 minus x squared over 2 plus a constant. And this is the solution to our integral. If you have any questions, leave them in the comments below. Otherwise, I hope that you found this helpful.